So we're going to look at a topic called reaction stoichiometry. So what is stoichiometry? Stoichiometry is the use of coefficients in a balanced chemical reaction that serves as a quantitative relationship between substances in a chemical reaction. Like the reaction shown here, where you have 2 aluminums for every 3 iodine molecules that reacts to produce 2 aluminum iodide molecules. This relationship we can use as a way to make stoichiometric factors that compare one substance to another in this chemical reaction. So I can make a stoichiometric factor of 2 moles of aluminum, which should then be equivalent to any other substance in this chemical reaction using their stoichiometric coefficient. So in this case, I could do 3 moles of I2, or I could even say that that is equivalent to 2 moles of aluminum iodide. Using these stoichiometric factors, we can now convert, using the technique of dimensional analysis, from one substance to another in a chemical reaction using this relationship of moles in our balanced chemical reaction. So far in this class, what we have been able to do is we have learned how to convert from mass to moles using the relationship of formula mass to the mole value. We have also learned how to convert from moles of something to molecules of something using Avogadro's number. And we also know that we can convert from molecules of a substance to the number of atoms in that substance using just the substance's formula itself. So we already know that we can do these things. What the balanced equation and the stoichiometric factor have now allowed us to do is to increase that relationship, but not only from one substance, but to another substance in a chemical reaction. So this might be the conversions we can do within a substance that we might call substance 1. And on the other side, this might be another substance in that chemical reaction that we call substance 2. The connector here is the connection of the balanced chemical reaction. So, I also want to point out that there are some other things that we have learned in this class that we could add into this graphic organizer that shows a relationship between moles and balanced reactions. We also know that, or have learned about molarity and density. And it turns out if we know the volumes of substances and their either moles or mass, we could calculate their densities and molarities as well. This is actually a very complete graphic organizer of the majority of the concepts that we have learned so far in chapters 1 through 4 of the OpenStax textbook. So what we want to do now is use these concepts and their connections in order to look at a chemical reaction and be able to assess the amounts of things or masses, the number of moles, their concentrations within that chemical reaction. So let's keep this graphic organizer in mind, and let's try some practice problems here. So this first problem we're going to look at is how to determine the mass of a substance. In our particular case, this is going to be O2, so we're looking at for the mass of oxygen that is formed by the decomposition of a particular value in mass of a reactant, in this case mercury 2 oxide. So the mass that we start with is 1.252 grams, and we're wanting to essentially figure out how much of oxygen is produced as a product. In order to do this, the very first thing you have to have is a balanced equation. So I have provided a balanced equation for you here in this problem, but you should always check before doing any stoichiometric calculations to make sure your equation is balanced, because if it isn't, you will not be getting the right calculated value. So how we do this is we start out with our mass of our mercury 2 oxide of 1.252 grams. And we're going to put that over a 1 to make it into a fraction. And if we go back and look at our graphic organizer here, essentially, if we keep in mind that on the right-hand side is our substance 1. In our particular case, this is going to be our mercury 2 oxide. And the right-hand side is our substance 2. That is going to be our oxygen. In order for you to determine the amount of mass of substance 2, we need to start with where we're at for substance 1. So we are actually given the mass of substance 1. In order to find the mass of substance 2, we need to find a path in order to get there. And what we do is essentially follow the arrows from square to square to get to from one block to the next in the shortest pattern. And it turns out that that is going to be following this path. And so what we'll do is convert our starting value of mass to the very next box of information, and we will continue doing that conversion until we get to the mass of our substance 2. So what we're going to have to do first is convert our mass to moles of mercury 2 oxide, and then using our balanced equation, we will convert from moles of one substance, mercury 2 oxide, to moles of our second substance, oxygen. And then once we have that, we'll move to our last block over to mass of oxygen using our formula mass. So let's try that really quickly. So the first thing we're going to do, again, keep in mind, is we're going to convert from mass to moles of mercury 2 oxide. And we will need the formula mass for mercury 2 oxide, which I've calculated to be 216.59 grams. And that is equivalent to 1 mole of mercury 2 oxide. And our masses will cancel out one another. And the next thing that we want to do is convert from moles of mercury oxide to moles of oxygen. And as we stated before, stoichiometry states that you can use the coefficient in value of moles as a relator from one substance to another within a balanced chemical reaction. So what we do is we use the coefficient 2 and the coefficient 1 in front of oxygen as our quantitative relator or stoichiometric factor to convert from one substance to the next. So we put 2 moles of mercury 2 oxide on the denominator, and that should be equivalent to 1 mole of oxygen on the numerator, and our moles of mercury have now canceled out, and we are now in moles of a completely different substance in that chemical equation. And so now we're in moles of oxygen. We can convert from moles of oxygen to mass using the formula mass. So for every 1 mole of O2, that's equivalent to 32.00 grams of O2. And when we do our math in our calculator, we need to keep in mind that this should probably be, you should also be keeping in mind significant figures. Our starting value is 4 sig figs. Our formula mass here for mercury 2 oxide is 5, and it's 4 for oxygen. Our stoichiometric factors of mole, quantitative mole relations are exact, so we don't actually use those numbers in significant figures. And since everything is multiplication division, we'll go with the lowest value, which is 4. And so our number, when rounded to 4 significant figures, ends up being 0.09249 grams of oxygen. All right, let's try this one more time. In this particular problem, example 2 says that what mass of chlorine is required to react with 10 grams of sodium. In the previous example, we started with a reactant value and calculated a product value. And in this particular case, what we're looking at is one reactant value. How much do you need of another reactant? The same principle applies here, so it does not matter if you're going from reactant to product, product to reactant, or within the same side of a chemical reaction, the stoichiometric factors still do the same thing. So it might not be a bad idea to have this graphic organizer handy so that you can map out your plan of how you plan on going from one unit to the next within a chemical reaction. So in our particular case, the beginning substance for this particular example problem is going to be sodium, and our substance 2 is going to be chlorine gas. And the value in units that you were given for your sodium was in mass, and the value or units that are asked for chlorine gas is also mass. So let's map out the shortest route to get from one place to the next, and that's through the mole calculation and balanced chemical reaction. So keeping that in mind, let's go to this problem. So it says that we start with 10.0 grams of sodium, and what we want to do is first calculate how many moles of sodium. So we're going to convert from grams to moles. So we need the atomic mass of sodium, which is 22.99 grams. You get that from the periodic table. And we know that that's equivalent to 1 mole of sodium. And now that we've canceled out grams and have converted from mass to moles, we can go from moles of sodium to moles of chlorine by using their coefficients in their balanced chemical reaction. So for every 2 moles of sodium, you have an equivalent of 1 mole of chlorine needed to react with it. And so that has given us a way to go from moles of sodium to now moles of chlorine. So we've now converted from one substance to the next. And at this point, since we have moles of chlorine, the question asked for what mass of chlorine is required. We can convert from moles to mass of chlorine using its formula mass. So for every 1 mole of chlorine gas, it's equivalent to 70.90 grams of chlorine gas, which is its formula mass. And knowing that our starting value is 3 sig figs, our atomic mass is formula mass is 4 for chlorine, then our smallest value is going to be 3 for significant figures. Our answer rounds to approximately 15.4 grams of chlorine gas. Okay, let's try this again with another problem, and this will be the last one that you have an example here. In this particular problem, it says what mass of sodium nitrate is required to produce 128 grams of oxygen gas. So essentially what they're saying here is we've given you some mass of oxygen, one of our products, in fact 128 grams of it. Let's back calculate how many grams was required to produce that amount of oxygen. So this time we're going from using a product value to now calculating a reactant value. And that's not any different than what we've done so far. But what I would do is go ahead and use your graphic organizer again and set up the graphic organizer so you know your path of how to calculate the substances that you're needing. So the substance 1 that we were given that has an actual numeric value with it was our oxygen gas. And in fact, it was 128 grams. And so we know that that's the mass box that we're in. And it asked for what's the mass of our second substance. And that second substance will be our sodium nitrate. Now, do you guys notice how I've put the product on the left and the reactant on the right? Does it really matter that we're doing that? No, it does not matter. I could have actually rearranged this where I called substance 1 sodium nitrate and substance 2 oxygen, and I would have just started from this side over here and moved to the right direction, figuring out my path. But it doesn't, so since these are essentially mirror images of one another, it doesn't really matter. So I just went ahead and started with the right hand side. We're going to plan our path, and this is going to be very similar to what we've done so far. We're going to go through the mole and the balanced equations to figure out the mass of our reactant. Okay, so we're going to start with 128 grams of O2. We will convert our 128 grams of O2 to moles of O2 using the formula mass. So 32.00 grams of O2 is equivalent to 1 mole of O2. And then now we're going to go from moles of one substance to moles of a next substance, and we're going to use our balanced equation and their coefficients for that. So the coefficient for oxygen is 1, so 1 mole of O2, and is equivalent to the coefficient of sodium nitrate, which is 2, so 2 moles of sodium nitrate. And now that we have converted that to moles of sodium nitrate, we can move that right into mass by using the formula mass of sodium nitrate. So for every 1 mole of sodium nitrate, that is equivalent to its molar mass, which is 85.00 grams. And when we look at our calculation and what kind of number of sig figs it should be, we have 3 for our starting value, 4 for oxygen's molar mass, and 4 for sodium nitrates. We're going to go with 3. And when you round this number in your calculator, you'll get 680. Now, 680 is actually written in this form as only 2 sig figs. So we have to make that 0 significant, and the easiest way to do that is just put a decimal there. That makes that significant, and we can put our units of grams of sodium nitrate. Now, if you are someone that does not like to have a hanging decimal, which some people are like that, and in math we've been taught to put a 0 behind that, well, you can't really do that because that would make that number 4 sig figs. So if you don't like having a hanging decimal there, you can actually make that number a scientific notation number. So if we move the decimal 1, 2 over to the left, this would be 6.80 times 10 to the second grams of sodium nitrate. This is an alternative way to write that answer, but both are acceptable. Thanks for watching this video. These are just examples of converting within a balanced chemical equation of mass of one substance to mass of another. If you wish to learn some more stoichiometric type calculations, watch the other videos on different types of stoichiometric problems.